Okay, good morning, folks. Great to be here. This is my first Clojure conference. I'm excited to be sharing my experience working with this library called Cortex, which I've worked with in the past 8 to 10 months. I am Kiran. You can call me Kiran. I work with a company called Datacraft Sciences. We do analytics and machine learning consultancy. And some of us at Datacraft have contributed to this Clojure library. So before we get started, can I have a quick show of hands on how many of you are familiar with machine learning? Oh, okay, good. So I'm going to have a lot of hard questions to answer. Great. Now I'm also going to make a sort of oversimplified explanation of machine learning for those who are unfamiliar with it. This talk doesn't need any prior knowledge of machine learning. Okay, so the outline of my talk is basically we'll talk about the basics of machine learning first, then we'll learn a bit about Cortex itself. We'll build some networks with Cortex, and finally we'll look at some recipes at how to understand what's going on in the network. Another way to read this is we learn something, we write some code, then we learn something more and we write some more code. So what is machine learning? I think the usual formulaic way of describing that is learning from data. And when we write a program, when humans write a program, we want to encode some rules, which is when X and Y happens, do Z, and when A and B happens, do C. And in some situations, the rules are very complex, they're too many, they change too quickly, and in those situations, we think it makes sense for the program to write its own rules, and that's what essentially machine learning is about. Now, machine learning is a really big field, so today I'm only going to focus on one small aspect of it, which is supervised classification. And what is that? So imagine you're a child and you go out, the first time you go out for a walk in the park and you go with your mom and you see something furry and you ask your mom, what is that? And she says, okay, that's a dog. And the next thing that comes along, you ask, what is that? And she says, that's a cat, and so on. And sometime later, somebody asks you, what is that animal? And you say, okay, that's a dog. That's exactly what supervised classification is. It sees a set of examples and somebody gives it a label, a dog or a cat. And after some time, we ask the system, what have you learned? Is this a dog or a cat? And we test it. So the only difference between a human and a supervised classification system is that humans just need 4 or 5 pictures of dogs, whereas a supervised classification system needs like 10,000 of them before it starts to really identify a dog. So of the many classification algorithms that are popular today, why are neural networks popular for classification? My personal take is there are 3 reasons. One is state-of-the-art performance. So on this particular task, which is reading the zip code on postal email, neural networks had an early breakthrough in 1992, and it was able to predict pretty well what are the handwritten digits, and it was used in a mail system at that time. Today, 25 years later, neural networks have gotten to 99.8% performance on that, which is supposed to be close to or better than human level performance. And incidentally, this data set, which is called MNIST, has gone on to become what's like the hello world of machine learning. The second reason is, I think, is flexibility. So neural networks for classification can accommodate several kinds of outputs. One kind is a single target, which is given a data instance, what is the label? So spam is a great example. Either the label attached is spam or not spam. Multiple targets could be, if there are multiple things in an image, for example, if there are 5 dogs, can it identify 5 dogs and 1 cat in that? And this picture is an example of what a multi-target classification is. So first of all, it's identified that there are 2 people. It's identified where they are, it's identified where their faces are, what their ages are likely to be, and what their facial expression is likely to be. So that's what multiple target classification can be like. And the third, which is quite interesting, is composability. And different layers in a network can be composed to create something new, and you can compose in a modular fashion, almost like Lego blocks. So this is a network called the image to text network, which I think is composed of two different networks. What it is doing is that given an image, it can generate a description of that image. So I don't know if it's really visible. The first image is like, the description is a person on a beach is flying a kite. And this is composed of two different networks. The first network creates a text description. Sorry, just list the objects in that image. So the first image would be beach, person, kite. And the network on top of that takes those three words and builds a meaningful sentence out of that, which is a person on a beach is flying a kite. And this is a great example of how two networks were composed to build a third network. So having learned what neural networks and basic machine learning is, let's look at what Cortex offers us. Cortex is a deep learning library written entirely in Clojure, which means that it doesn't wrap an underlying Java library. It's got a data-centric interface where the network itself is a sequence. The network consumes sequences to train it. On each run, it generates a new network. The way it builds the network is by wrapping maps of maps into the network. So we'll see more about that later. It's also quite performant and it's memory efficient for training on GPUs. So as a background, neural networks now perform much better on GPUs than on CPUs. And it is quite important to be efficient memory efficient while training on GPUs. And Cortex does that quite well in comparison with certain other networks, with say ResNet, which is a very popular network for image classification. For those of you who have an interest in image processing, Cortex supports convolutional networks, which is a kind of network which is important for image processing, like image classification. It also supports ingestion of certain pre-trained networks. So why is this important? So now, today you have networks that takes weeks to train on large GPUs, and having built those networks, you want to be able to leverage it somewhere else. So you build the network, say in TensorFlow or Keras or a different toolkit, and you don't want to retrain and spend all that time building the network. So you can just use that network and ingest into Cortex and then use it here. Finally, it's got some abstractions for targeting different kinds of underlying architectures. So you can have two kinds of implementations libraries on a GPU. One is CUDA and the other is OpenCL. So because of this abstraction, it makes it easy to really port or build an implementation for the underlying layer. Great. So now let's look at some code, how to build some simple examples, some simple neural networks in Cortex. The first one is predicting room occupancy. So let's imagine your customer is a building management company and they want you to tell how many people are in a building. Have is about 8,000 instances, and it basically contains some measurements. They are light, temperature, humidity, carbon dioxide in an office room. And the goal is to predict when the room is occupied or not. Very straightforward, single label classification. This is what the data looks like. They're all numeric fields. There are no categorical fields. And finally, the last column is 1 if it is occupied and 0 if it's not. So the first stage is to ingest the data. And we basically read the CSV file and we generate data in a form that Cortex will be able to consume And what is that? That's basically just a map. Each data instance is a map which has two keys. One key represents the input, and the other key represents the target or the output, whether a room is occupied or not. Next, let's define the layers. So a network can be composed of many different kinds of layers. We'll take it layer by layer. The first layer takes 3 arguments, which is similar to the XYZ dimensions of a cube. So for the input layer for this network is basically saying I have 5 inputs, and the Y and Z doesn't matter because it's just a 1 dimension. This is what the code looks like, and it's saying that look for the key in the map where the key is data, and we can see that data has got 5 inputs, and when the network trains, it pulls out that as it gets fed a sequence of maps. This is the entire network definition. We first defined the input layer. We added a few more layers. Each of those layers does some kind of computation. And finally, the last layer will predict whether the room is occupied or not. This is what the network looks like, the schematic. Each layer is connected to the next. There are multiple connections between each layer. And the last layer is a logistic layer. So it generates a probability whether the room is occupied. The probability of the room not being occupied is just 1 minus that. Next, we get to the training stage, and we train it for 10 epochs. An epoch is a term used to signify 1 pass on the data set. So if the network gets to see all 8,000 instances once, that's called 1 epoch. So we do that 10 times. And so we call the train function, and it takes a few arguments. It takes a description of the network, which is the sequence that we saw earlier. And it takes the train and the test data sets, and we can give it some additional parameters. We are saying that train just for 10 epochs. And after 10 epochs, this network trains really quickly. In a few seconds, we see that it's given us, it's printing some statistics. It's saying the loss is this much. So the loss is a term to measure how well the network is trained. Lower the better. So we can see the loss is quite low, 0.03, which means that it's done a pretty good job at training. Last, we evaluate the results. So right now, we are only concerned about accuracy. And we test the accuracy, and it shows that the accuracy is 94%. So we can go to our building management company and say, okay, we are 95% sure about telling you if one person is in the room or not, but given the whole data set, given all the people in the building, we're 95% sure how many people are there. We'll move on to the next example, which is something we have seen earlier. This is recognizing handwritten digits. And we can see that humans have a lot of diversity in their handwriting. They like to express the number 2 in many ways, the number 7 in multiple different ways, and that's what makes it challenging for a machine to learn. So we'll first define the network, and here we can see that the input is slightly different. So when we look at an image as an input, we can think of it as a 3-dimensional image or a 3-dimensional cube. So there's X and Y, which is the length and the breadth, and it's also got a depth. If you have 3 colors, RGB, that's a depth of 3. If you have an image that has got literal depth information, say from a camera that's capable of measuring depth, then you will have one more field, a 4th field. So in this case, we just have black and white image, so it's 28 by 28 by 1. Next, we'll define the entire network. In this particular case, I've used a standard network, which is used for image classification. It's got about 11 layers, and each of those layers has got some layer-specific parameters as arguments. Next, let's look at how training is going. So Cortex provides a couple of ways in which we can get a pulse on what's going on inside the network. One is the confusion matrix. So confusion matrix is basically a representation of how each digit's training is going on. So for example, if we look at the number 9, we can see that maybe 96.5 is right. And we can also see how it is being incorrectly classified. So we can see that 9 is being incorrectly classified as 3 in multiple situations. So if we hover the mouse over any of these numbers, we get a constantly changing description of what are the misclassification is like. So 7, for example, is being misclassified as 2 because it has got the upper part of the 7 looks like 2 in many cases. We can also look at the graph of the loss, which is an indicator of how well the network is training. In this case, for those of you who are seeing it the first time, the network has trained quite well. It is making less mistakes over time until it proceeds till maybe the 80th epoch, and after that, it changes its mind. And this is another example of what's inside the network. So we can see how the layer weights are changing. So for those of you who have used neural networks before and are thinking, why is a slide on TensorFlow here? Good question. This is not TensorFlow. This is just the UI. It's Tensorboard, and Cortex is capable of pushing its event so that you can use Tensorboard as well for understanding what's going on. Great. So that wraps up a quick demo of how easily you can build a network in Cortex. Next, let's step back and understand what goes on when we build a neural network. And the key to the success of neural networks is this algorithm, which is the backpropagation algorithm. So when I think of analogies for backpropagation, one that I find quite relevant is any kind of game that involves shooting at a target, which is archery, darts, golf, for example. So it proceeds in this way, where you look at what's in front of you, you look at where the target is, and then you aim, and then you shoot. And then, for example, in archery, the target is far away. You can't quite figure out if you hit it or not. So you go close to the target, and then you see, okay, I'm maybe 2 inches away from the target, and I have hit it a little to the left and below. So the next time I need to move up and right to go close to the target. And the artifacts involved, the glossary of backpropagation can be explained in the same way. So we have a forward pass, which is literally pulling back the arrow and shooting. And the backward pass is going close and getting feedback on how well we did. Did we do well? How far are we? And the loss is basically at the end of the competition, when we have shot 10 arrows, we get a score, how well have we done? 3 have hit the target, 5 are nowhere to be seen, and 2 are maybe halfway there. So that gives us a combined score of what loss is like. And finally, we have the gradient, which is giving us an indication of which direction we should move. Should we strike it? How should we go closer to the target? Is it right? Is it left? How far? Are we really close to the target or not? So having talked about the terms, let's see what the theory is like. So this is my personal experience report of how I have seen how neural networks is taught in theory and in practice. Right? So the theory is that you often learn by, you understand backpropagation, and then you write a toy implementation where you take a small matrix multiplication thing, you write the matrix multiplication, you can compute the gradients, you multiply it back, and so on. And now you have understood what goes on. And now you use a toolkit that you're familiar with, one of the open source or other toolkits, and you have so many layers available to you. You can stack it up like Lego blocks. This layer this layer has got 100 inputs. So the layer below that should have 100 outputs. So you just basically arrange your layers, and you sip your coffee and watch your loss function decrease. So a good loss function looks like this. It's like a very good student. It makes less and less mistakes over time, and all's great. However, the reality is quite different, right? backpropagation, in the words of this researcher who's very familiar with backpropagation, is it's a leaky abstraction. So although you have built this tower of nice layers, all of which respond very well to backprop, the problem is each of them has got different quirks. They train under certain circumstances. They don't train under other circumstances. So what you're likely to get is a loss function that doesn't behave. This loss function, for example, is like a heart rate monitor. And this one, it likes to train for some time and then it changes its mind, jumps back up, and eventually just doesn't behave at all. There's a nice page that shares interesting or artistic loss functions that people have found, and even the experts basically give up. They say, we don't know what's going on here. It's not training. That's all we know. So the point I'm trying to make is that a lot of the time, I think there are two situations. One, if your data is very similar to a network that has trained on the data that you have, you're lucky. Your training goes really smooth. You give your data to the network, and you're done. You get a great downward sloping loss function. Other times, you are not sure what goes on, so that the training doesn't happen. You search on Google and you find articles that say 37 ways your network doesn't train. And then if that doesn't work, you basically generate a bunch of random networks. You leave it running on the weekend and you come Monday morning to office and see, okay, what's gone on? I mean, we've tried some stuff. Let's see how it's behaved. So I think the key is debuggability of a network is a really crucial feature. So in most libraries, what's happening is that you have a few rules going on. If A and B and not C. So if there's a bug, you go in and see the code, it's done. But in the case of neural networks, there are hundreds and thousands and sometimes millions of parameters that are changing every time. And it's very hard to know what's going on in that engine. How is the fuel flowing between different layers? Is there somebody chewing on the pipe because of which your engine is stalling? So there are two ways in which neural network toolkits make it possible to understand what's going on. Most of the time, they give really nice UIs, which has lots of graphs on what each layer is doing, what are the inputs to this layer, and what are the outputs, and so on. But swanky REPLs are not as common. So this is my experience from working with a couple of toolkits and with Cortex. And what I've observed, now this could just be my observation, is that with other toolkits, I need to keep going to the documentation a lot. So is it like, okay, this network has this layer. So this layer, there are hundreds of classes, and each class has got, a constructor properties, and some other methods inside. So how do I really debug what's going on? And I found that we are familiar with all the idioms of functional programming, and why not just use those idioms? Why build a very complicated interface to know what's going on in the network? So I'll just take three examples. You know what pure functions are? So pure functions are basically a function that takes an input, returns an output, and has no side effects. That's exactly what a layer is. So it takes an input, generates an output. We know what reduce is. It takes a sequence and generates a single output. And a neural network basically is a sequence of layers. Each layer takes an input, generates an output, passes it on to the next layer, and finally we have the output generated by the whole network. We also know what iterate is, where we take a function and repeatedly call that function on an input. And that's what training is. It takes a network and generates a new network when it runs, and we keep doing this for some time. So having looked at these idioms, let's see how easy is it to do REPL-driven development in Cortex. So let's try and query some of the network properties, like what are the layers in a network. Often we don't start by building networks from scratch. We are given some network by somebody else, or we take a network that we know might work very well. So The network is just maps of maps of maps. So we can use get in or the threading operator and query, what are the layers here? And it will tell us, okay, these are the 5 layers. There's a linear layer in the middle, and there's a loss at the end. How are these connected? We can query the edges. And the edges returns a sequence where each sequence tells the source and the destination of a network. Now, this is a very simple network where each layer is just connected to the next one, but you can have networks that skip layers or that have multiple heads and so on. So using this information, we can easily create a graph. We can draw a graph of what a network looks like. In most situations, it's not needed because the network is too big. How could we examine the weights in a layer? So again, MNIST, it's got many layers, it's got many weights. So we can run a function that says just print the layer summary, and that's just syntactic sugar gathering all the data from internal maps. And it will give this kind of an output. This is just a snippet of the entire network. These layers have got these biases, it's got these many weights, and we can see that it's got 850,000 trainable parameters. So this is something that should concern you if your memory in the GPU is less, then you want to know, is this network going to fit in memory or not, or is it going to cause delays in swapping in and out? So I was concerned that I have 850K layers. Where are these layers? I mean, where are these weights? Are they distributed evenly across all layers? So I just plot it, and I see that the 11th layer has got most of the weights. The rest of the layers don't have much. So what I might want to do is, if I'm concerned about memory, I reduce the parameters in that 11th layer, see how it trains. If the network is doing decently well, I can just manage with that. I don't need to really have 800,000 parameters in that particular layer. How
and see what's going on. So here I'm interested in the loss, and I want to see what's the cross-validation loss. And you can see that it's 2.2 to 1.6, so it is learning, but it is not doing a great job at it. It's pretty static. And the first one is nil because the first network has got no data. I mean, it's got no loss. It's 0. If we want a more complex example, we want to see how a network has changed over time. So this particular layer is the convolutional layer, one of the convolutional layers in the network. And usually when a network is initialized, its weights are initialized in a small range, and as it trains, the weights at that layer change. So it's getting better at recognizing, and therefore it's changing. And here we can see the older generations, which are in the older generations are light and they are far behind, they are more pointy, whereas the newer generations are spread out, they are in the dark color in front, which is a good sign. It's telling us that this particular layer is training well. So sometimes what happens is we have a big network, some of those layers train, and at some point there's a choke point where the information is not going to the layers below that. So there we can see those layers don't train at all, their weights stay the same. So we can use this to understand who is choking the network or which layer is choking the network. Last, we can use listeners. So listeners are like pure functions. You can call any, do some diagnostics there. The typical things you do is you want to save the network. So networks tend to go up and down as they train. Some get worse, some get better. And when you get good performance, you want to save that to a file. Or you want to kill the network kill training because it's performing very badly. And if you have, say, 100 networks to train, you might want to say, okay, let's move on to the next one. So we can do this with listeners. And you've already seen examples of two listeners earlier in this talk. The two UIs, both the Tensorboard UI and the web app of Cortex are both listeners. They're just taking some data and piping it to the web app so you can visualize it. So what we have learned today is Cortex is a great library for building neural networks in Clojure. It can do feed-forward networks. It can do convolutional networks, which is great if you're doing image processing. It's also highly performant. It works well on GPUs. So yeah, I'm pretty excited about how Cortex has grown. It was open sourced just less than a year back, and it's got quite a few contributors, about close to 30 contributors today, and it's getting close to the 1.0 release. How you could help Cortex grow? Adding support for recurrent networks. So this is a kind of network used for sequences like text. And if you want to do text in Clojure, but Cortex doesn't have it yet, you can always use a Clojure wrapper of deep learning for J. There are also Clojure wrappers of Java wrappers of TensorFlow, which you could use. What's also not there is support for more recent network structures. So we have network structures, new network structures coming out literally every week. So Inception is a very well-known network structure. So adding support for some of these would be a great value. Ingesting all kinds of pre-trained networks. So Cortex has support for some networks such as ResNet 50, but not many of the newer ones. So adding support for that would be great. And automatic differentiation. So automatic differentiation is what allows you to give any kind of function, and the network will figure out how to differentiate and give feedback to that particular layer. Thanks to the Think Topic team, which is behind Cortex. Chris is one of the leads there, and Mike, who's with Datacraft, who's also one of the most senior contributors to Cortex. And finally, if you'd like to play with some of the notebooks that were used to generate some of the code for this talk, this is the link. Thank you. Any questions?
Great. So, questions? So, like, how do you compare with this the Python library? What is that famous Python library? DLL.
TensorFlow. There are many. Okay. So, I think there are two aspects. One is that TensorFlow right now is at a stage where if somebody doesn't know anything about machine learning, it's pretty much press play and it will work. Now that is for things that have been solved by TensorFlow, where you know the network very well, the data is very similar to that network. So to answer the question in a different way, some time back, if you wanted to do deep learning in Clojure, you didn't have a choice. You had to jump out to a different language or toolkit and then integrate in a messy way by having some kind of a web service. So now this is an option that allows you to do at least feed-forward network and convolutional networks in Clojure. Certain exotic network types are not yet supported, so for that you would need to use TensorFlow. From a developer's perspective, I found that with TensorFlow, I need to open the docs a lot because there are hundreds of layers. Each of them is a class. Each of them has got different kind of attributes. In this, I mean, literally, this is not to diss Cortex, but it didn't even have API documentation. So I'm just at the REPL querying what's in this map, what's in the map after that, and I'm just able to graph and see what's there. So I found that very interesting to work with, very easy to work with. So it's not an apples to apples comparison. I think TensorFlow has got probably tens of hundreds more contributors and is vastly more stable and robust.
Any more questions?